Hey everybody, Adam Savage here in my cave with a show and tell involving Buster. I know it's nightmare fuel, but this was the 6th host of Mythbusters. Buster was a hybrid 2 crash test dummy built for testing human reaction in car crashes. And while it looks like nightmare fuel to you here, in fact, there's a huge amount of really vital engineering going on inside of a crash test dummy. And we went to our local friends at Lumafield, where they use their portable CT scanner to help us peek into the interstices of Buster. Let's go there. All right, Eduardo, every time I come to see a scan from this, it feels like Christmas.
Yeah.
And we gave you some really fun crash test dummy parts. I'm just off the bat, I want to ask, like, what did you think about these parts when we first sent them over?
I think this might be the grossest thing I've ever CT scanned, and that is saying something. But
and we haven't even tested it for what is still extant on the surface of this thing.
But just the kind of cold, clammy, you know, there's something otherworldly about these crash test dummy hands.
Well, and this is the literally OG Buster hand from 2003 from our first season.
Yeah.
I can't remember which explosion caused the total failure of this part, but it happened literally very late in the series, like 2013 or 14.
Okay,
yeah.
All right.
So
long life.
We've got
you can see the there's some welds and some repairs. And
yeah.
It seems like maybe there was a little bit of rework over the years.
Yep, I think this whole middle part was, I think I machined a piece of that and it was re-welded in, and then
nice.
This is a tertiary weld repair.
Yeah, yeah.
But now we get to see on the inside of this guy.
Yeah, so we scanned this, and you know, there's a lot of really interesting stuff you can see. I think, you know, if you didn't know better, you might think that was an actual hand, and then you get a little lower and maybe you start to freak out a little bit.
Clearly, it's an Android hand.
Exactly, right. One of the cool things about CT scanning is that we can start to isolate materials. So this, you know, this is the overview of all the different materials here. But then we can hop to this bookmark over here, and we've got just the metal pieces. So like you were talking about.
Yeah, there's a little clevis with these 2 pieces here.
Yeah, that's right. So here we've got the welds, and we've got this this bolt that's going through. That would be this piece right here, and then there's there's kind of something else in there that's sort of holding everything else in place. And then we can also sort of cheat the translucency a little bit, and you know, you can start to see that section that we're talking about, just right in here, where those metal pieces come together, holding the polymer, you know, all in one place to kind of, you know, simulate that that real hand. And then here's sort of a cropped view where we kind of cut a slice through, so we can start to see where that interaction is happening. So I'm guessing this is probably, you know, stuck in, and then they're sort of clamping after this has been molded separately. I'm guessing it's not an over-molded piece. There's probably like a totally separate sort of mechanical clamping that's happening
you're probably right.
to hold this onto the joint itself, which is fascinating. You know, I was reading about crash test dummies, and it turns out that they've been making these the same way, at least this model, since the 70s.
Yeah.
And all of the different specs and details and actual construction methods are specified because they have to be the same across different crash test dummies made for different manufacturers and different applications.
Right.
And so they actually pour materials that were common in the 70s that are no longer common today. They use the same manufacturing methods. So, you know, today we might see an overmolding operation would be more common.
It's simpler.
But in the 70s, that maybe wasn't as common for those materials, or even possible with those materials. So this clamping would have been the way that they attached this softer material to this harder material.
And they haven't gone through the quality testing to see how new processes might fit the process.
Well, really, it actually has more to do with like data traceability and the ability to say, like, we did a crash test with this, you know, series 2 of dummy or series 3 of dummy, then we know that that data is going to be the same as the data that we did 10 years ago with another series of the same. So they haven't changed those things quite as much.
Oh, that's really
so it's really
cool.
an interesting place where, you know, I think as an engineer, I'm always torn between, I want the latest and greatest tool, and I want the like most tried and true and tested method of doing something.
It's that article that comes up like once a year on tech sites about the fact that we're still using COBOL in banking.
That's right, exactly.
And airplane reservations because they're bulletproof and it won't fail.
It doesn't fail, that's right. And I think we see that here. You know, this is, obviously this is an older dummy, but I think if we went and scanned, you know, some of the more recent ones from the same series, they would be almost identical. It'd be impossible to tell the difference.
By necessity.
Maybe minus the 10 years of wear and tear from you know, Buster's use. But,
and some of the burning parts.
That's right, yeah. Maybe that's not quite standard operating procedure for as many things.
Now, speaking of burning parts, we also did the leather face. He's gone through untold abuse and fire, and Carrie Byron did this amazing stitching job
Yeah.
bringing him back to. Oh my
Those are some
God!
incredible repairs.
That is so horrifying.
Yeah. So yeah, it's really every time I've seen this scan on someone's computer in the office, I am just horrified.
It's very upsetting.
And I don't know if the scan or the actual object is more terrifying.
That's fascinating. I was wondering if this would be slightly boring as a scan, and nope, not even a little
Not at
bit.
all. No. You know, in terms of the materials and everything, there's not as much going on as there is in that hand, obviously, but. You know, it's fun even to see, like, there's this section at the top, if you flip that over, where this material is maybe compressed a little bit more.
Right.
And so there's a different density that we're seeing here.
Oh, that might have been from an actual concussive impact.
Exactly, yeah. So if you're hammering the material down over time, and it's densifying, it starts to show up as, you know, a different color in this view of the scan.
So this could be evidence of how many times we dropped Buster on his head.
Yeah, I bet it's more than one.
It's definitely more than once.
I think it takes more than one to make something like that happen. And then we have the same kind of cropped view where we can kind of look at a slice of it. And even here, you know, you can kind of see the darker section of that compared to, you know, the lighter section in the nose still
where it's really
squishier.
dimensional.
Yeah, exactly.
That's also can be really invaluable to be able to see the actual thickness wherever.
Yeah.
Oh wow! Look, you can see the stitching on the inside.
Yeah, all the stitching is there. If we go back to the overview, we can see. You know, we can zoom in. We can see all the strings and everything else. It's incredible to be able to reproduce in so much detail. You know, an object like this. If we were trying to do, you know, other kinds of 3D scanning, it'd be very hard to get that kind of detail and things that are hidden behind other things. It's
especially with undercuts and everything. So
right.
I have always described making as a process of a virtual and an actual, and the virtual part is me putting the object into my head.
Okay.
I can't make something.
Yeah, loading it into your mental RAM.
Until I can put it in and spin it around, and that's often the difficulty of communicating with other engineers.
Yeah.
I'm finding every time I look at one of these scans, it's giving me an insight. So I'm wondering if your experience with these machines makes you, do you think, even better at seeing through the insides of things?
Yeah. Yeah, I think you get a new appreciation and intuition for how things work. You know, the reason I became a mechanical engineer is because I was fascinated about the way the world worked, right? Yeah. How do physics turn into reality? Where does that theory that you're talking about meet the road? And you know, that exhibited itself through education and work and all these different things. But really, this product has really brought that into a focus that I've never had before. And I think for me, one of the most surprising things about building a CT scanner hasn't been the difficulty of the hardware or the software. You know, we have great engineers doing all these hard things. It's actually been, when we talk to our customers, they have an emotional response to seeing the data. And you would think, you know, why is that the case, right? Like, if you're looking at this scan of a hand, it's cool and it's interesting and we can kind of geek out and nerd out about things, but there's a person that spent, you know, months of their life trying to figure out
with this object in their head, in their lives,
and
trying
they didn't have this technology. They couldn't really, they could think of it in their head, they could design it in a computer, and then it would be made. And they're always, it's kind of always gnawing in the back of your head, like, did this work the way I was going to? But there's this emotional resonance that you get with, like, I can see something that I've never been able to see before.
This was the first bit of highly specialized engineering that we wheeled into our narrative process.
Yeah.
And I managed to get a still desiring to be unnamed government agency to give me a Hybrid 2 dummy. And then our first experiment, we exceeded all of its specs and shattered it.
Okay.
We shattered its pelvis.
Right.
We broke a leg off. And that almost felt like a badge of honor.
Okay.
We thought this would solve all of our analog human problems, and in fact, it was just gave us a glimpse into how difficult it is to figure out how dangerous things are, to calculate, you know, 700 G hits. Yeah. So for me, the emotion this carries is seeing the internal structure of something that feels a little like a Mythbusters origin story. We didn't think of it as an engineering show or as a science show.
Right.
We didn't think of it as an educational show. We literally were following our noses through these narratives. And in the final analysis, we get that it is those things.
Right.
But it starts with playing with toys like this.
Yeah, exactly.
You know? And I love the ingenuity that goes into, we weren't able to supply a bigger crash system, but when you have all the stacks of rubber and steel
all the
that
materials
make up the responsive body of the thing, it's fascinating.
Yeah, and all designed to be pushed to a limit. And then I think, you know, I can certainly resonate with that idea of what is it like to go beyond that limit? You know, how do you push beyond that? As an engineer, that's what we're always thinking about.
Well, and on the show, we were always trying to, every meter that you can buy simply wants to tell you when you should leave the room. Yeah. There's very few meters that tell you when you're dead, but that's always what we wanted to measure.
Right. Exactly. And crash test dummies are the same, right? They don't need to endure a load that much further than what a human being can endure.
Which blew my mind, because our first jump, we dropped it from 170 feet and endured a 700 G
oh my gosh.
load when its standard operating is around 7. It's an order of magnitude off.
And you don't really need to do a detailed scientific analysis of like what would happen if we dropped a person in 700 Gs, they would die. It would be over, right?
100%.
So you don't need to design to that case.
Wow. Okay, we have one more object that is still in the it's the most elaborate of the 3.
Absolutely.
It's in here.
Yeah, let's take a look.
All right.
Great.
It's the child's head.
It's the child's head.
So I did a gig for a how do I say this? Basically, I was doing a gig and there was a bunch of crash test dummies, and I asked if I could have one of the child crash test dummies, and it was given to me.
Okay.
And it's an analog to a 10-year-old. So
you got the whole thing.
I have the whole thing.
That's
I just let you guys the head.
Okay. All right. Well, we might have to come back for the rest of it. This is really fascinating. I think, as much as we could see a little bit of the details in the hand, there's so much more to dig into here. So this is the 2D X-ray view of that head. So we're just looking at an X-ray projection. If you went to a doctor's office, you'd get the same kind of image. And the way the CT scanner works, we take hundreds or thousands of these images and then turn them into those 3D models. But this is really cool because in many ways, this is a lot like how our customers would use this system, right? Maybe they're a company that makes the head of a crash test dummy, and they want to know if they're seating the sensors correctly, or if those bolts are seated in there. Or maybe they have a problem with some of the molding processes or something like that.
Right. I hadn't thought of it as part of QC, but of course.
It really is. That's the number one use that our customers have. Is there's sort of this whole phase called new product introduction, where you've designed the thing, you've made your prototype, it works. I think when you're building side projects and you're building art pieces, that's sort of the pinnacle moment. And then you have to how are we going to make 100,000 of these? And so then you need to start validating suppliers and materials and work instructions and all these other things. And that's the piece of manufacturing that really slows companies down. And that's why we started Lumafield, was to help companies that want to take a product into production move a lot faster, because they could have the confidence that the things they're building, like we talked about earlier, the things that are invisible that they can't see, but they know exactly what's there. So they can tell their customers, when you crash this crash test head, it's going to work the first time, and you can be sure of that. And we can give them that kind of confidence. So that's really the vision for Lumafield and why we started the company.
Oh, that is so fascinating. Can we investigate the scan?
Well, let's look at the inside for just 1 second.
There he is.
Yeah.
Can I grab it?
Go for it. Yeah, absolutely.
Right. Hello, buddy.
I haven't stuck any heads in here before, so it's a bit of a first.
Seems so innocuous. It's surprising how heavy heads actually are.
Yes, it really is. It's a lot of poundage for sure.
About 7 pounds, I think. Yeah.
Wow. But yeah, it's great. You can stick things in, run the scanner, and then get the data really quickly, which is what our customers really love about the technology. And you saw that, right? It's just sitting here on this this little platform of foam. You don't have to do any complex preparation work or fixturing or anything like that. You sort of jam it in and go, and that speed is really pretty unprecedented.
All right, can we get into it?
All right, let's get in. Let's get in.
Yeah.
Cool.
Oh, all right. So, I can see just from the outside, I can see various screws holding parts together. There's a plate on the back. Before I even look at this, I know there's a plate on the back of the head that fits a sensor in there, a transducer. And I can also see that there's like an internal hard skull on top of which is this fleshy outer layer.
Right. Yeah, and I would assume this is probably, on my side, that there'd be some way to service this, and maybe it's possible to remove this out section if you've damaged it in some way, sort of like what we saw with Buster. But it's hard to tell until you can really sort of dig in there and take it apart. But we don't have to do that. We can do that with a scan. So here's our head. Outside view looks the same. But then we go to translucency. And actually, my assumption was totally wrong. I was really surprised when I first looked at this scan that this doesn't seem to be an easily removable kind of outer layer. Maybe you could flex it off, but
maybe pull off this way.
Something like that. But there's a lot going on here, and it seems to me like there's this harder, more dense core material, and there's this sort of softer, more translucent, with the way that we're viewing the image here, sort of fleshier section. So really, I guess this is the skull, right, on the inside, and this is kind of the analog of the.
And this is thicker than I thought it would be, actually.
Yeah,
to be honest,
it's pretty thick all the way around. You can kind of see right up here, but I would have assumed it would have thinned out a bit. But
yeah, it's like almost half an inch. It's like 450 pounds.
Yeah, it goes kind of all the way back. The nose, especially, is like pretty beefy.
And I mean, this is what I love thinking about from an engineering standpoint. Is that's the result of decisions made 50 years ago.
Yeah. Totally.
A set of decisions. Right. Oh, so now is this?
Yeah, so this is, if we kind of
oh, look, oh, neato.
Yeah, and then we crop it. So this is kind of cut in half, and then we're seeing the inside. So here, there's some kind of like bolt that's like attaching the skull, this like central cavity into these other pieces. There's another bolt down here. There's another fastener. There's a few different fasteners that are kind of holding things in. Yeah. And then, I think of this as really the business end of any crash test dummy. This is where the sensor goes. Okay. So back here, you can take this plate off. There's these 3 screws here, and then you're able to seat some kind of sensor.
Pop that off.
There we go. Right.
So the sensor goes in there.
Yeah. So you take these screws out, and then you'd be able to put a sensor on the inside, and that would be able to sense the force that the crash test dummy sees whenever it goes through,
and
whatever
force this way,
hellish life it's about to have. Yeah. Right, exactly. Yeah.
And look, and that's all hollow.
Yeah, right. And so there's a whole hollow section in the middle here, and then we've got this sensor back here. And we actually zoomed in on the transducer because it's such a particularly interesting piece. And one of the interesting things about CT scanning is that you can see inside of things, but if you have a lot of different kinds of materials interacting, it can be pretty tricky to get really, really fine details.
So was there was a transducer in here?
I don't know. I don't think there's it's hard to say. I think, with the scan it is the way right now, there's some kind of puck. So maybe there's just something that's like filling the space. We should take it apart and find out.
Yeah, let's totally take it apart. Do we have an Allen set?
I have to say this kind of feels like cheating. Usually we don't get to take the things apart.
Okay.
Oh, here we go. So there's a weight back there. So that's where, so then in here, there's a weight here. But then look, there's like a little channel here, which is where the wire would go.
There you go. Right.
So there's the hollow section. There's the big puck. If we go back to this cropped version, we can see the different material there. We can see one of the screw heads back in that area.
Wow. It's even labeled rear.
Yeah. Monodirectional weight.
Okay. So it looks also like something may have slid in here and secured through there.
Oh, interesting. That makes sense. Oh, and then there's like a nut or a washer or something. Yeah, there's a washer that's been like pushed forward. So that makes sense. So then probably there's a module that goes in that has the sensor package.
And easily removable.
And then the wire comes out here, and then that goes into some sort of like package on the inside. But then this is interesting that this is a weight, because that is probably like it's counterbalancing to make sure. I bet this makes up for the fact that there's some of this hollow space there.
Yeah.
I bet this is like a center of gravity sort of calculation that would have been done to figure out what size weight that would need to be.
Again, all of these decisions made 5 decades in the past.
Yeah, exactly.
That is really...
And you can really tell too, right? Like this weight is just a rectangle with some holes drilled in it, and then there's like a punch mark in it.
And someone has stamped rear in the back.
Exactly.
Yeah, I mean, that is, and this is cable.
Cable, and there's an arrow pointing forward.
Wow.
Cable goes that way.
Amazing.
So the sensor, that's not in this one. It's something we wanted to look at a little bit more. So we actually we picked one up. We actually have the kind of sensor that would go into a crash test dummy.
So this is a scan of, wow, the resolution is insane.
Right. So we've got the scan here. We've got the wire leads coming off the back, and then we can go in and start to look at the insides, and then we can get a lot more detail about how this actually functions. And the way that I'm guessing this works is that it's a Wheatstone bridge, which is a system where you have 4 resistors, and 3 of those are set resistance values, and then the 4th one is a variable resistor. And as that resistance changes, you can then, it'll change with different forces or different temperatures or different deflections. And so you actually just measure the change in voltage across this circuit. Depending on the change in resistance, the amount of force that's being experienced. Okay. So here you would just have a data logger measuring voltage going through this circuit. Right. And you would just put that into a table, and then that table would tell you this many volts equals this many G's of force that you would get. And that can be happening super fast, and it's very inexpensive, and it's very reliable. And these Wheatstone bridges were actually created in the 1800s for the first time. Yeah.
Really?
So this technology is tried and true for sure.
That is so cool. I had no idea it was that old.
Yeah, it's been around for a long time. Electronics, there's some pretty clever people working on this stuff a long time ago.
Tell me about the upper limit of your resolution. How much detail can you get out of the traces?
Yeah, so with our scanner, we can, if we really set the scan up right, we can get down to 40 micron.
Wow.
Yeah, so really, really tiny, traces. We can do that with fine features in circuit boards, but we could also do that with really thin walls in a medical device, for instance. If you really wanted to have a membrane or something that you wanted to be able to actuate that was hidden inside of something, we could test and see what kind of wall thickness we're able to get there. And then obviously if you just want general resolution and accuracy, it's nice to have that fine feature resolution as well.
And I would assume that's improving all the time.
It's interesting. Resolution is one of those conversations where we want to continue to push the limit, but we don't want to do that in a vacuum. We don't want to just continue to build a more expensive system just because we can.
Right.
We are really driven by the needs of our customers. So when we talk to our customers, if you're scanning this dummy head, do you really need 20 microns?
Right. Yeah,
do you need to go fast? Maybe not. And if you get down to small enough level of resolution, you have to start worrying about things like seismic activity and the temperature of the air and the barometric pressure and the temperature of all the different components, and are they going to scale up and down? So it creates a much more expensive and difficult to operate system.
Interesting. Okay.
So we had a long conversation with hundreds of people about for months at a time as we were developing the equipment, how much resolution do we really need to be able to serve the kind of customers that we're working with? Because our goal is to get this technology in the hands of every engineer, right? So we could make it 100 nanometers. We could go crazy, right? We could build something in a lab, and it could be, we know how to do it, but that's not the thing that gets this technology in the hands of thousands more engineers than have it today.
That is totally fascinating, and I love the post-facto view, fly through the interstices of the thing.
It's always fun to kind of compare the scan and the reality of the inside, and if it's what you expect or not.
It's so cool.
Yeah. We have a lot of fun scanning things and turning them into these digital files, but sometimes we like to go back to the physical world. So we actually 3D printed on one of our desktop 3D printers a tiny little shrunken head version of Leatherface there.
Wow.
And we wanted to see if we could capture the detail. It's kind of always fun to stress test the scan and the printers and kind of see how they work with each other. But it's so much fun. You can see the stitching, not just on the outside, but if you flip it over.
No way, really?
Yeah, you can actually see all the stitching on the inside as well. It all came out in the model. You can see the mesh. The entire thing is there.
Oh my God! Can we have this one?
Or please, that would be great.
God, I'm going to send this to Carrie Byron. She did all the stitching.
We might have one more thing that you might be interested in. So we did it on our desktop 3D printer, but then we phoned a friend, and we did the full size replica as well.
Oh my goodness!
So we've got the 1-to-1 there.
Wow. Oh my God, yes.
And you can really just see all the details of, the little
burnt,
ripples.
peeling
and,
apart.
Yeah, you can see the stitching. I bet it's all the same on the inside too. Yeah, so we've got the 1-to-1.
That is so thrilling.
Even little knots and things are all coming through.
I'm not even sure why I'm so thrilled by seeing that, but it is remarkable.
It's possible, but then seeing it in person is a totally different thing.
Well, also I know that there's no real scanner that could get all
I don't know how you would do that, right?
Detail.
The fact that you've got the detail that's like underneath the stitch, right? I don't know how you would do that with any other kind of scanning technology. Wow. This isn't really what I thought we would do when we started the company, but I like to find new uses for the technology. So certainly our little, our family of heads is kind of a fun little artifact of this whole process.
Oh my gosh, this is such a satisfying object, I can't even. Oh my gosh. Dude. What I love about this is how far from, I thought we were just looking at the inside of something with a scan. The fact that that information can be parcelized and turned into 3D prints opens up whole new ways for me to think about these scanners. And Eduardo said the company he thought he was building in the beginning is not the company he has now because the customer needs have changed so much. You want to fly through Buster's head yourself? Well, you can. There's a link in the description below to the actual scan we made of this face and all the other parts.